58 years after it was first proposed, string theory remains the most famous candidate for a unified theory of everything. It's the ultimate mathematical framework for all matter and forces in the universe. But its reputation is polarizing. Critics like physicist Sabine Hossenfelder describe it as an undead zombie, a theory that refuses to die despite a lack of empirical evidence. This frustration stems from how physics traditionally works. In a top-down model, you propose a theory, make a prediction, and test it against observation. String theory breaks that model. The math requires 10 space-time dimensions, allowing for 10 to the 500th power universe configurations. It's a landscape of solutions so vast that no one can find the specific configuration that describes our world. Even if we knew which configuration to look for, the strings themselves are billions of times smaller than anything we can detect. This means the prediction is physically untestable. This physical dead end has trapped the field in a forever war. Researchers are left with a beautiful mathematical model, but no physical way to prove it exists in reality. Recently, physicists have opened a new angle of attack, called bootstrapping. This method reverses the direction of the entire search. Instead of starting with a complex theory and trying to force it downward into reality, bootstrappers start at the very bottom. They build upward from empty space using only basic logic. They begin with a rule called unitarity. It's a pillar of quantum mechanics, stating that the probabilities of all possible physical outcomes must always add up to exactly 1. Next, they add Lorentz invariance. This enforces the basic, unbreakable symmetries of spacetime, ensuring the laws of physics look the same to all observers. The core assumption is that these baseline rules remain true even at the highest, most chaotic microscopic energies, the ultraviolet regime of the universe. By applying these unbreakable rules to empty space, the goal is to see which physical models are mathematically forced into existence. Researchers like Cliff Chung at Caltech and Hanuret Alvang at the University of Michigan have recently put this bottom-up method to the test. They added simple mathematical constraints to the foundational rules, like ultrasoftness, a requirement that prevents energy from concentrating at infinitesimal points. They then calculated what happens when these particles crash together at extreme energies under these strict logical conditions. Out of the infinite ways particles could theoretically scatter, only one specific mathematical pattern survived the calculation. That pattern was the Veneziano amplitude, the exact formula that birthed string theory back in 1968. By simply enforcing the baseline rules of quantum mechanics, the math naturally and inevitably forces particles to behave like strings. String theory emerges as a structural requirement of the mathematics itself. These findings change the rules of the string wars. The debate has shifted from a question of observation to a strictly legalistic mathematical argument. To disprove string theory now, critics must mathematically prove that one of these baseline quantum assumptions is actually false. There is a significant caveat. These papers use toy models, highly symmetric versions of physics that don't yet perfectly match our messy real-world universe. However, string theory keeps appearing as a special mathematical object. Researchers from various fields keep getting led back to these same equations from different directions. As physics pushes toward the absolute limits of the microscopic world, modeling the universe as a collection of simple points appears increasingly inadequate. The quantum universe continually demands extended objects like lines and loops. String theory appears to be an inescapable foundational feature of nature.